Hello, for this tutorial we're going to be covering heap allocation versus stack allocation, as well as regular pointers as you'd see them in a language like C++ or Galaxy from StarCraft 2. Now, when we've been working with pointers before, we've always been working with pointers as if they were a handle or some sort of struct pointer. And if you didn't realize this before, struct pointers collide with each other. So if you have two different structs, you could have a pointer 1 for one struct type and a pointer 1 for another struct type. So you could have two pointer 1s that refer to two different struct types, and they could both exist at the same time. With normal pointers, the pointers never collide. They're always unique, because rather than using a bunch of scattered arrays and continuing to allocate from those, it uses one super big array. And that array might be the RAM or the hard drive, but it's a super massive array. And it actually has two allocation styles. There are two. And the first way is the way we've been working with, which is the stack. And we've just been working with lots and lots of small stacks that are scattered everywhere. And this stack is useful for allocating single integers, not sequences of things. And if you notice from languages like C++ and so on, you can't pass arrays into functions. You can only pass pointers to arrays and functions. And in vjass, you can't pass arrays into functions. You can't pass linked lists into functions. You always pass a pointer to a function. And so those pointers have to be pointers. They can't be full arrays or anything, because the arguments are allocated from a stack, much like this stack. And that means it can't allocate sequences of data. If you look here, it's allocating 1. That's why the instance count is raising by 1, because one thing is being allocated. And you can't allocate more than one thing at a time. When you use a heap, you can allocate more than one thing at a time. But the thing is, couldn't we increase this to like 50 or something and allocate more than one thing at a time? What's wrong with that? Well, that would work until we come back to the recycler. How do we recycle those huge sequences? Well, couldn't you just take from the top and see if it's big enough, and then if it isn't big enough, allocate a new instance? Well, that'll work, but you continue to take from the top and make the sequences inside the recycler smaller and smaller until you have a whole sequence of ones and they're all defragmented. And then eventually you'll have an overflow error because you can't recycle any of those sequences. You can't reuse any of them. They're all too small. So the thing you have to be cautious about is, number one, you always have to make sure the biggest sequence is at the top, which is what a heap can ensure. And number two, you have to have a way to defragment those sequences. A heap doesn't necessarily ensure that, but you can use an array with little Boolean flags to ensure that. So you can have a little array here. Let's do an array. Private static Boolean limit. Boolean array limit, and then you can have like a local integer pointer 1 equal 5 and local integer pointer 2 equal 15, and this will be the last index of the sequence and the first index of the sequence. So it goes from 5 to 15. Which means that it has 11 indexes to it, not 10, 11. You also have to include the 0, which is the 5 in this case. And then you could do set limit pointer 1 equal true and set limit pointer 2 equal true. And then when this stuff is deallocated, you can go if limit pointer 1 minus 1, then combine. So if the pointer directly to the left of the deallocate pointer, in this case pointer 1, is a limit, so it's the end of some sort of sequence, then you can combine those two sequences together, just thus defragmenting it. And then if limit pointer 1 plus pointer size, which in this case is 11, then combine. So if the right side is a sequence, combine the two. And that works absolutely brilliantly. It ensures defragmenting. And you could do that with stacks, but again, the problem is how do you ensure that the first element in the stack is always going to be the biggest sequence? To ensure that, instead of using a stack, you use a heap. A heap's a little bit more complicated than a stack, but it ensures that the first element is always either the biggest element or the smallest element in the entire heap. A heap is what's called a tree. And a tree essentially has 3 pointers instead of 2 pointers. If we remember from lists, it has a next and a prev. A tree has a parent, a left, and a right. So if you had something like a parent node or something, you could have a left side and a right side, and then it could just keep going left, right, and so on to form this pyramid. And it just keeps going down and down. A heap is typically mapped to an array. It doesn't have actual pointers. Instead, you do math to get to the specific slot you want to go to. If you want to go up, you do this divided by 2. If you want to go left, this times 2. If you want to go right, this times 2 plus 1. I'm not going to go into why these operations go to those specific positions, because this is not a tutorial all about heaps. I'm just going to show that that's how you actually read a heap from an array. Problem with an array, though, is that it's statically sized. And that can be a challenge with heaps. You'd have to know the size you want the heap to be, and it would have to be that exact size, and you could never go over that size, otherwise you'd have an overflow error. In vjass, it's simple because your heap's always going to be a size of 8,192. That's the array size, so you don't have a choice, and that's usually plenty big enough. But in C++, if you just went with 8,192 and you only need like 10 slots or 15 slots or 500 slots, you're wasting a lot of memory there. You're a huge chunk of memory that's wasted and that's never going to be used. So heaps are generally made with what's called vectors. And what a vector is just a pointer to an array. So it points to an array, and then when you attempt to read from a slot that's bigger than array, so let's say array.size equal 50, and you do array 99 equal to 233 or something, it will create a new array, so allocate, let's say, an array size of 100, copy all the elements from the old array to the new array, so we'll go array.copy new array, or rather, you get the point? And then it will deallocate the old array and store that new array inside the vector. And what I personally use for the increasing size is like I increase it by 20%. So I just do array size times 1.2, and I'll do an R2i there, since indexes need to be integers, and allocation sizes have to be integers. And that works out. So then you can have a heap that will continue to grow as you need more room. But if you notice, when you resize the vector, you have to copy all the old elements to the new array. And so that's kind of the weakness of vectors, that huge copy operation. And plus, the reads and writes are going to be a bit slower because you're doing these if statements on each read and write to make sure it's in bounds. And if it's not in bounds, remake the array. And you're also going through 2 pointers rather than 1. You're first going through the vector pointer, then you're going through the pointer to the actual array. So 2 pointers instead of 1. But they're generally used over arrays in C++ because they're pretty much dynamically sized arrays, however big you want. And then you can resize them to a specific size, and they're pretty much the same speed as arrays in C++, because just reading a pointer isn't all that slow. But they do have their weaknesses. In the malloc library I have right here, the thing that uses heap memory allocation, it actually runs off of a hash table, which is even slower than a vector. It uses a hash table because a hash table can pretty much take an integer of any size and it will always stay to a particularly small size. You could pass in 3 million if you wanted to, and it would still maybe have a size of 3 or 4. And it also doesn't have to continue to copy old elements to new elements. It doesn't have to remake itself over and over again. The weakness with a hash table, though, is that it has to hash that number into a smaller number, an ID, that fits into an array, or something like a B tree. And we'll not really go into what B tree is. Now, if you notice, it doesn't read like an array or anything. It hashes a number, it does all this other crap, and then it finds the correct value and then returns that value. So it has to do all this stuff. It's not even done in like one iteration. It might be a couple of iterations because it has to find the value. And so this is actually why hash tables get slower as you plug more values into them. And the vjass hash tables are no exception. This is actually why I use my own little hash table in here rather than use Bribe's table library. Because Bribe's table library is just one hash table for the entire map. So everything's plugging values into there. So that means it's going to be the absolute slowest hash table you could possibly use. And here I'm going to be dealing with a lot of values. So I want the hash table to at least be a little bit relatively fast and not be bogged down by everything else in the map. So that's why I made my own in there. Now if we actually look at the heap a little bit more, right here, heap, we'll notice that the heap has a size. And then here are the operations to get the parent using the little math I told you about. And then two very special methods here, the bubble up and bubble down. When you store an element into a heap, like 5 or something, the insert method looks like size equals size plus 1, set heap size equal to new element. So in this case it'd be storing into a hash table, normally it'd be storing into a vector, and then call bubble up size. The bubble up essentially sends that element from here at the bottom to as high as it can go until the two elements, or rather the element above it, is bigger than it is in this case. We wanted a heap that would keep the toppest values, or rather the biggest values at the top. So this bubble up is going to send a value up until the value above it is bigger, until the parent is bigger. If we look at the loop here, it's comparing the parent pointer size to the current pointer size, the pointer that was passed in, which is what I just said it would do. And it will also stop if there is no parent, so it will stop if it's at the very top. The bubble down does the complete opposite. It will stop when the two values below it are smaller than it is. So it'll go down as low as it can go and then stop. And right here I have bigger, so that's actually not quite right. It should be smaller. So if the left is smaller than or equal to the pointer, or if the right is smaller than or equal to the pointer, stop. Rather, if both of them are. So there's a little fix I just did. 1.005 now. And so that will go as low as it can go. And here's the insert, which I just said. Link just links the pointer position to the heap position. And that's useful if you want to be able to remove any element from the heap. And then here's the remove, which does a bubble up and a bubble down, because any position might be removed. So it might be going up, or it might be going down, or it might be even a combination of the two. If it was always going to the very, very top, it would only be bubbling down, which is what it normally happens with a heap. You normally only ever remove from the very top of the heap. And they're used like priority queues. Priority queue keeps the element with the biggest priority at the front of the queue. So you always implement those with the heap, and you just do a simple pop command. And what the pop command does is reads from the very first position in the heap, removes it, and then puts the last position to that first position, and bubbles that last position down as low as it can go. So if we look here, I'm reading the very last position. I'm putting that last position, so there's the last position, I'm putting it into the first position, or the position that was removed, and then I'm bubbling that position down, or rather that pointer down, as low as it can go and as up as it can go. So that's the typical remove command for a heap. Here's the defragment I talked about earlier, keeping the sequences within the heap as defragmented as possible. Languages like C++ and whatnot will do a pretty decent job with this. They're not going to have a huge Boolean array or a byte array of Boolean arrays for every single element. They're going to do it as compactly as possible. They don't want to waste any memory whatsoever. So they're going to have defragment schemes that will still have somewhat fragmented memory, and it won't be able to do anything about that. There are actually two schemes for defragmenting that Microsoft C++ uses. One is the standard defragmentation, and one is the smart defragmentation. The smart one doesn't get as defragmented, but it's still not perfect. This one right here does actually use a Boolean array, so it is perfect. So it will keep everything as defragmented as possible. Nothing will be defragmented in here if it can help it. And if you deallocate every bit of memory you have, if you allocate the entire maybe 8,000 indexes and you deallocate all those 8,000 indexes in whatever order you wanted, you'd only have one element left in the heap, and that element would be the sequence of all 8,000 indexes in proper order, because this is a perfect defragment method. Now if we look at the allocate method for memory, it's going to be a little bit different from the stack. Here we're reading the top of a heap, not the top of a stack. And then there's the normal enabled. And then here we're making that the array size, the sequence size you want, is not less than 1, because a sequence of 0 or some negative sequence doesn't even make sense. That's not even possible. Smallest you can have is 1. And then over here, if the heap, not the stack, is empty, or in this case, this is new, the first element in that heap, which is the sequence, is not big enough to allocate this array, then it's going to allocate new memory here. So if the sequence retrieved from the heap was size 15, it had 15 indexes in it, and we wanted an array of size 30, 15 is not big enough. So new memory has to be allocated. And the heap, once again, this very first pointer up here is always going to be the biggest sequence in the entire heap, now that I fixed the bubble down algorithm. And over here, the deallocate. And let's not worry about this stuff for reading from a heap. All this literally does is take out a chunk of the sequence that was retrieved. So if the sequence was size 30 and we wanted an array size of 15, it'll only take out the first 15 indexes from that sequence. And this actual specific if statement will take the entire sequence out. So over here, it removes that pointer from the heap completely. Over here, it changes the pointer in the heap from the first pointer to pointer plus array size. So it shifts the pointer over. That way, a chunk of the sequence is taken out. And then here the array size is set. Now in the deallocate, rather than throwing it into a stack, it throws it into a heap. So if we look over here, this stuff over here is just for defragmenting. So here are the limits I talked about using the array. And then here are the memory sizes. And if you notice, memory size is stored both at the first index and the last index. Memory size is not array size. Memory size is actually the exact same value, but it's only stored in the heap. And this is because array size only needs to be stored at the first instance, which is the pointer itself, and memory size needs to be stored at the last instance and first instance, the pointer and pointer plus memory size minus 1. So last instance of the sequence. The reason it also needs to be stored at the last is because in the defragmenting, when we're looking on the left side, we're looking at that last pointer there, and we need a way to get to the very first pointer of that left sequence. So if we had sequence here and we wanted to look at the left, it's left out last that we're looking at, and we need a way to get to left out first. So we have to know the size of this left sequence. We only have this to look at, so we need to store that size into both the left and the first. And in the same regard, at right dot first, we need to be able to get to right dot last. Now over here, we're throwing that pointer into the heap, then we're defragmenting the heap. If we go down here to the pointer, all that does is set the memory type. So you have lots and lots of different memory types down here: Boolean, string, integer, etc., etc. The interesting thing about memory types is that in a regular programming language, let's even use Galaxy as an example since that does memory correctly. The smallest thing you can allocate is a byte. A Boolean is actually a bit. So an integer is 32 bits, and a byte is 8 bits. So an integer would actually be 4 bytes. And everything is always a byte. So you allocate, 3 bytes, 10 bytes, 50 bytes, you allocate in bytes. So an integer would be allocating 4 bytes. A Boolean would be allocating 1 byte, and a byte would also be allocating 1 byte. So notice that the Boolean actually wastes 7 bits there. So what you normally do if you really, really want to save as much memory as possible, you'll allocate a byte as a Boolean array of size 8, and then you'll read specific bits out of that byte and set specific bits to that byte. And that's actually what I do in the malloc for Galaxy, because Galaxy can only have a very specific amount of memory. You can't make too much, otherwise your map will die or whatever. In vjass, your memory is unlimited because it uses a hash table, which is nice in that's unlimited, but bad in that's ridiculously slow. And really, it would be nice if Blizzard even just put a heap into Galaxy that you could use, just like the heap I have here, or the heap I have in the Galaxy version of this. But they can't be bothered with that, so oh well. So now that we know what pointers are like, when we're actually dealing with a pointer to an array, like let's say a local integer pointer, or we'll call it I is equal integer pointer dot allocate 50. This I will be some value. It will be the pointer to the first index in that array. So let's say it's 1. And it is in fact 1 because that's the first thing that's been allocated from malloc. If we wanted to access an instance from that array like I35, that would be equivalent to saying I plus 35 or 1 plus 35 or 36. And that's exactly how arrays work in C++ as well, or in Galaxy. All they literally are is typecast pointer plus offset. So it might be unit pointer plus offset or whatever. And that typecast will read the next certain amount of bytes so that it conforms to a certain data structure. So for an integer, it would read the next 4 bytes. For a unit, it'd still read the next 4 bytes because a unit is just a pointer, which is an integer. A handle is a pointer. But a handle can't be used as an integer. That's kind of the big difference between handles and pointers. Pointers equal integers, awesome. Handles not equal integers, why would you use a handle? Typecast safety. If you just have regular pointers that could be integers, you could typecast it to whatever you want. With handles, you can't really typecast them unless you add specific functionality to typecast from one handle to another handle. So that is why Warcraft 3 and StarCraft 2 uses handles instead of pointers, because typecast safety. If you remember that whole fiasco from before where you could execute bytecode, that was bad typecast safety from the return bug, H2I, I2H, etc. So let's move on. Let's try saying I35 equal to 50 and then call print I35, and we'll go ahead and see that it displays 50 right there, 50. So nothing new there. Now what if we wanted to have our own data structures, you know, like in a struct where you have certain fields. So it's, well, actually they're called unions in regular languages. Unions can only hold fields, which are variables. Structs can hold fields or methods. Same with classes. But a union, once again, can only hold variables. So let's just stick with the union. vjass does not have unions, but things like C and C++ do have unions. So if we have like unit integer I, real x, and how about unit u, real r, when this union is allocated, what happens is it allocates 4 bytes for the integer, 4 bytes for the real, and then 4 bytes for the unit. And so this turns into 12 bytes. You could also think of it as an array. So you have, well, no, don't think of it as an array yet. So we'll just say it's 12 bytes. And actually it would be an array, so it would be like a byte array of size 12. And if byte. So what are these fields here referring to then? These fields are actually constants that refer to the offsets. So this would be constant equal 0, this would be constant equal 4, or size of I, and this would be constant equal to 8, or size of R, plus size of I. And so this real would read the next 4 bytes, 4 through 7, this would read 0 through 3, and this would read 8 through 11. So there's the entire array. So unions are extremely compact. When you have something like a struct or stack, or rather a struct or a class, rather than doing it this way, they have to actually deal with inheritance. And so what they'll end up doing is they'll have like a pointer 1. If, let's say, we have this as a struct instead, and struct A and B extends A, you'll first have an A, and that will be the first 12 bytes, and they'll have whatever fields down here that it wants, other fields for other bytes. So it has this extra pointer in here. The reason for this is so that you can have multiple extensions, so you can have A, C, D, E, whatever. However, in newer languages like C# and even in vjass, you can't have multiple extensions. And as you see, there are actually 2 ways to possibly extend. One way is doing a pointer to that type, and the other way is doing the fields directly inside. So you'd have integer I, real R, unit U. You just input those constants directly in, rather than having a constant that pointed to other constants. And then other fields for other bytes. So now to get an idea, a better idea of how all these constants work, let's try creating our own struct from scratch. And what we're going to do is create like a struct A, extends array, and struct. Now we're using malloc for this, so this struct is not going to have any variables inside of it. Absolutely none. Instead, it's going to have properties, or things like those offsets I just talked about. So we're going to have constants, private static constant integer. How about we call this a list, or how about a node? And it will be a list node, so private static constant integer next equals 0, so that'll read index 0. Private static constant integer prev equal 1. And so now we have a mapping here for an array. And we could just pass any old array into it. We could typecast any array into this, and it'll read it just like this. And that's how regular C++ does it as well. It just reads it into the structure. And if it attempts to read something out of bounds, like if we had node2 extends array, and that had something like this, and then we had a node, and we tried to typecast it to node2, that would work until we tried to do .head. Or how about .head? This .head would be out of bounds a node only has 2 instances, and that .head tries to read the second index, or rather the third index. So that can be one of the dangers of typecasting. You end up reading instances that are out of bounds. Now for malloc, what we're going to end up doing here is creating a pointer of pointers, an integer pointer array, so an integer pointer that points to an array of integers, and those will in turn point to specific pointers. The other thing we could do is typecast those integer pointers into whatever type we wanted using the typecast method here. So each type here has a typecast right there, and it just typecasts a specific pointer into the certain type. So we could do either one. What I'm going to do for now is just an integer pointer that takes pointers, because a node has a third thing here down here, integer data, and that's going to be mapped at 2. So let's get rid of node 2 here. Next thing we have to do is add the actual variables in, and those variables are going to be method operators. So method operator next takes nothing, returns this type. Return integer pointer this next. Then method operator next equal take this type, new next, returns nothing. Or how about this type pointer? Set integer pointer this next equal pointer. And we can just keep going with prev and data. So prev, data, 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 prev, and then we can even do an allocate here. So stack method, allocate takes nothing, returns this type, return integer pointer dot allocate 3. And there, now we have a fully working union. Notice, well, struct. I guess it would actually pretty much be union here because this only has variables in it. This is just a data structure, a way to read an array, or a way to interpret an array. So it could be any array of size 3, and this is how it's interpreted right here. It interprets index 0 as next, index 1 as prev, and index 2 as data. And the allocation is always going to be 3. And you could actually have structs extending other structs by interpreting it the same exact way, but with extra fields in it. So it could have the next 0, prev 1, data 2, and then maybe a head 3. And normally data is going to be at 1 here because for stack pointers they only have a next here. If you have it this way, you'll break your inheritance. And this is actually another reason why things like C++ use pointers to data structures that interpret it a certain way rather than putting those interpretations directly into the struct. It's because it allows you to organize it however you want instead of being confined to organizing it something like this so that you don't break everything else. Makes it so you don't have to think ahead. It makes things easier. It does waste memory with those extra pointers. It does make everything a bit slower with those extra pointers, but that's why they do it. So if you don't have the extra pointers, it has to be organized this way. Here's your stack, here's your list. This way you can typecast a list into a stack. If you don't have your extra pointers, it can be organized however you like. So here's your list, and then your stack would be just a pointer or something. And in fact, the node would not have these interpretations in here for the stack. It would not have data, and it would not have next. It would only have prev equals 0, or rather prev equal 1, and then private static constant integer stack node equal to 0. And then over here it would do the previous next, here's the next, and this would do integer pointer this stack node. So the stack node is actually stored in the node. You have extra pointers here like I said before, and then do stack node dot next. So here's one pointer read, here's another pointer read. And then here in the allocate it would be size 2, and you'd actually store some stack node into instance 0, and this would be private. That's how inheritance works in C++ and so on. So now you know 2 ways to do inheritance. This way, which allows you to organize fields however you want, but wastes extra memory and is a bit slower. And then the other way, which allows you to use as little memory as possible, but confines your data structures and makes everything harder to do. I personally use the harder to do way because I try to save as much memory as possible, but if you're doing multiple inheritance, you really have to do it the pointer way. You have to store those different pointers inside the other pointer, like pointer 1, then pointer 1 dot super 1 equal to pointer 2, pointer 1 dot super 2 equal pointer 3. So parent, actual pointer. And then when it tries to read something from super 1 or super 2, it goes pointer 1 dot super 1 dot field or whatever. So the 2 pointer reads there and the extra memory used here. So now let's go ahead and let's go ahead and take a look actually at a linked list. I've actually written a lot of collections here under collections, and here I have module collections, which are done the normal vjass way. If we look at one, stack module, here we have an array, and we're just spamming the heck out of arrays, more arrays, lots of arrays, variables, and so on. And then here I have a circular linked list, and if we look into here, there are 0 variables in here, there are 0 fields, there are 0 arrays. In here, once again, 0 fields, 0 arrays. You'll notice that in all the things that use malloc, there are going to be 0 fields and 0 arrays. The only thing that you're going to have in those are constants. Now, linked lists and so on don't even have constants because I'm using a special tool here for object-oriented programming, which is located in malloc. And let's go ahead and take a look at that tool. So here we have extend nothing. All that does is start up a prop count, and the prop count is the number of properties you're going to have, the number of fields you're going to have. This way you can organize them right, so you can have prop count parent plus whatever for your subproperties. Then you have extending from a struct, and here we do prop count is equal to the extended struct prop count plus the current prop count, and then allocate once again for prop count. And then down here you have create properties, which is just the method operators, and these can create properties of any type. Almost any type, actually. What you'd really want to do here is probably a typecast around this to the specific return type when you return it. For example, when we looked down to, let's say, the ability array, we can typecast it using the typecast method. We can take any specific pointer and typecast it. So rather than reading an array here, it can just be typecast this plus property ID, and that should probably be changed. That way you can have an array that's like, let's say the first instance is an integer, the second instance is unit, and the third instance is an ability. And I will probably change that in just a moment. If we go down here to nodes, here are all the nodes. These nodes contain the actual properties here. And they use the create property, which just creates the method operators I talked about. And they bind the name to a specific constant offset. So that's all these do. And they are literally just unions. And the structs up here, if we go back to the top, they use these unions. So the structs don't contain any properties, they just use the unions. The vector, though, I believe, has its own properties inside of it. Yes, it does. So here's one property, here's another property. They're both the same. One's just public and one's private. And if you remember what a vector is, it is a pointer that contains both a size, or rather it's just a pointer that points to an array. That's all it is. So you go through 2 pointers instead of 1. And here I'm saying that array to an initial size of 5. And then when it attempts to read, if the index is bigger than the size, set size equal to size times 1.2, increase it by 20%. And then set the index. So I'm not doing it though over here, so I should probably fix that as well. Finding lots of bugs, I see, and design flaws. So now you should know how regular memory works, how memory works in C++ and Galaxy and so on. And if you wanted to, you could even write your own allocation schemes and your own memory all from scratch and do it just like I said. You can write your own unions in assembly if you wanted to, or in pure C code without actually using unions, and you could do some pretty whacked out stuff. Well, that concludes this tutorial on general memory and memory management. I don't recommend using malloc for vjass. This is more for just learning how memory actually normally works, if we're getting used to that stuff, because if we looked over here, the linked list, there's no array in here. So when you're initially working with a linked list in C++ and you're going, what do? I can't use an array. I can't just give it a next either, because you'll have all these extra fields in it for regular lists. You'll actually have to create another class or struct or whatever called a node, and then you'll have to use that node. So the list head properties, or rather, if we look at this, you'll notice that I'm using both nodes as the actual nodes that have these specific values in them, and then I am using list heads. So in the allocate, this should probably be listhead.allocate, but whatever. But the list head has first and last. It only has 2 pointers to it, and then the node in this case has 4 pointers. Node.next, node.prev, node.head, and node.data. And the interesting thing about the list head is actually it has 3 pointers to it. It should not have 2, it should have 3. And the third pointer is the sentinel right here. So that is yet another thing I'll have to fix. And the first pointer here is bound to next, last is bound to prev, and sentinel is bound to data. So you could actually convert, like up here, a list into a node without any problems and do node equal node.next, and it'll still work perfectly. And you could even do node.data to get the sentinel for the first node if you wanted. So you can typecast freely between them. The list just won't have a list.head. So if you try to access that with the list, it's going to throw an error at you. So yet another thing I'll have to fix. But hopefully you got a lot out of this tutorial. Hopefully you'll be able to actually make a C++ linked list now without wondering what you're supposed to do, without being able to spam arrays. And hopefully you'll now see exactly how much memory might be wasted or might need to be used with every little allocation you do. And keep in mind that when you have things like methods in C++, or rather virtual methods, these are methods that can be overridden, keep in mind that these two are pointers, that they're also integers. And they also have their constant offsets. And so when you do like a size of in C++, which tells you how many bytes a class or whatever is using, it's not going to just return the size of for your variables. If you have any virtual methods in there, it's also going to return the size of for those. So it's going to be a bit bigger than you expected it to be. And if it's extending from other things, it could be returning the size of for those things it extends from. I'm not sure how the Microsoft C++ does its optimizations, but it could be that for single instances, it does its optimization like the first style, where you actually map things out one after another like in a union, and then union 2 extends union 1, so you just continue down. If you're doing multiple mappings, multiple inheritance, then it will do it the second way, where it actually uses a pointer. And really in C++ and so on, there aren't even classes. It gets rid of all those constants and just inlines them all directly, so you don't have ways to interpret data anymore. So if you have a typecast somewhere, it will just get rid of that typecast and replace it with the specific constants. And that's what's nice about Microsoft C++, is it optimizes everything away pretty much. Even the GNU one does it pretty well, but it's not as good as the Microsoft one. So that's why the GNU one's a bit slower and uses a bit more memory. Anyways, that concludes this tutorial, and hopefully you learned a lot.